Hi, welcome back. In this lecture I will describe the curl equation and the introduction of edge elements to solve a vectorial equation with the Fem method. So far we have been discussing basis functions only for scalar equations. For instance, we solved the Poisson equation, that is a scalar equation. And we have been using piecewise linear, nodal, and piecewise constant basis function. To deal with the vector quantities, such as electric field, the first attempt might be to expand each vector component separately in a nodal basis function. So this will be probably our first approach. We take in 3D our vectorial equation that consists of three scalar equations, and then we would apply the Fem method to each of our scalar equations. However, this doesn't work. It turns out that such an approach leads to non-physical solution, referred as spurious modes. We already saw when doing the finite difference method arising spurious mode. So in this case we will have to deal with the spurious mode, so we need to find a solution to that. A solution to this problem can be the usage of edge elements, which are very well suited for approximating electromagnetic fields. The basis function for edge elements are constructed such that their tangential components are continuous across elements, and we are going to look at more into detail of this. So while the tangential components are continuous across the elements, their normal components are allowed to be discontinuous. So what are curl conforming elements? So the edge elements are also called curl conforming elements. And the reason for that is that the continuous tangential components imply that the curl of an edge element does not contain a delta function at the element boundary. So if we calculate the curl at an element boundary, the solution doesn't contain any delta function. So this is the definition of curl conforming. For this reason, an electric field that is expanded in terms of edge element as basis function has a curl that is square integrable. In this lecture, we're going to use the edge elements to solve the curl equation in the frequency domain. So I will show that how edge elements can be applied to solve the curl equation for the electric field in the frequency domain. So this is the equation that we're going to solve. Here we have curl and curl, and then we have just one equation depending on E. So here we are in the frequency domain, so we have omega and j lowercase, that's the imaginary number. So together with the governing equation, this curl equation in the frequency domain, we have two boundary conditions. So one is a Dirichlet boundary condition and the other on the surface L1, and then we have a second boundary condition that is called the Robin boundary condition on the surface L2. Robin boundary condition is just a combination of Dirichlet and Neumann boundary condition. So we use these two boundary conditions just for be very general. In practice, most of the time we are going to use just the Dirichlet boundary condition for a perfect conductor. So we have both Dirichlet and Robin boundary condition on different surfaces L1 and L2, and Js in this case is an imposed source current. So the first step to derive a formulation for the Fem is to derive the weak form. As you know, in the Fem method we don't solve directly the governing equation, in this case the curl equation. However, we solve something that is similar to that, something that is true in the average sense, in the integral sense, that is called the weak form. So we proceed along similar line as in the scalar problem. We take the scalar product, that is integral, and test function wi, and integrate over the computational domain S. We do two things to work out our weak form. So the first is to apply a vector identity that is the curl of the curl that is corresponding to this expression here. So here basically we have dot product for this quantity and this dot product for this quantity here. So that's the first vector identity we are using. We also employ the Gauss law to work out this term here. So basically the divergence, the integral on the surface of the divergence of the vector f is equal to the flux of this quantity in the enclosed surface. So if we go back to the original equation here, we take this equation here, we take the integral and multiply by the test function wi, and then we apply to this term here, we apply vector identity, and then we also apply the Gauss law. The final result is this expression here. So this is the weak form formulation of our curl equation, and this is the equation that we're going to solve with the Fem. The major difference from the scalar problem lies in the choice of the basis functions. We use here the element basis function n, I in bold, so these are vector quantities, instead of the nodal basis function phi, as we use in the scalar problem. So here notes that is wi are vector quantity, right? And we're going to use our nodal basis function n that are also vector. So let's look at more into detail what is an edge element. So edge elements are associated to the degree of freedom to the edges of the mesh rather than the nodes. This is why they are also called edge elements. Therefore, we have to number all the edges in the mesh and also give the reference direction. So the technique is the usual. We have domain and then we divide in each element. In the plot of on this slide, we see representation of one element, so our element E. So as we saw before, we have our element, in this case might have index 1, that are going to be associated to a number of nodes. In this case we use a quadrilateral for a square, rectangle as the shape for our element. So our element E is associated to 4 points 1, 2, 3 and 4. So the edge element introduced the so-called reference direction. So we have 4 reference directions, 1, 2, 3 and 4. They must be counterclockwise. So the edges, as we saw before, are labeled by integers 1, 2, 2 and here and E. And we expanded the solution of our electric field as the following. So we use a sum from 1 to NE, that NE is the number of elements. And then we are using the basic function capital N in bold, that is a vector. EJ is the tangential electric field along the G edge in the direction of the reference direction. We are using Galerkin method. The Galerkin method is when we use the basis function as a test function or a weight function. So in this case we follow the Galerkin methods and choose the test function Wi equals to the basic function Ni. And then we substitute the state function in the weak form of the governing equation. This gave us a linear system of equation A multiplied by Z equal to B. So A is our matrix that can be calculated by calculating this integral here, Z is our unknown that corresponds to the tangential component of our electric field to the reference element, and then B is the vector containing the source term. It will contain this part here. So we'll have a part coming from the source and a part also coming from the boundary condition. So what we're going to do here is basically derive all the coefficient for our matrix A in this form here, and then we can derive also our source term, and then we solve the linear system to calculate the Z, that is that vector with all the components of the electric field. Just to give you an example, we can calculate the edge elements on a Cartesian grid. So for simplicity, we first study edge elements on a rectangular element. So our element is this rectangle here, and then we're going to have four edge element, each one for each of the element. Each one for each edge. So in this case, we have 4 edges, so we're going to have 4 basis function. So we're going to have 2 in the x direction, so in the x direction, and 2 basis function in the y direction. So let's look at the first basis function associated to the first edge here. And so this interpolation function is around the x direction, and the variation is in the y direction. So this is the one. So we have our vector, and that is in x direction. The intensity of this vector varies linearly with the y. So it will be if this is y 0. It will grow as increasing the y direction. So it's small and then linearly increase until when y is equal to the coordinate of this edge here. The second element is in the y direction, and is the intensity of this vector depends on x in a linear form. So you can see here is going to be in the x direction, and we're going to increase linearly. The same applies for the n3 and 4. So one will be in the x direction, but with the opposite sign. The other one again will be in the y direction with the opposite sign with respect to the this one. So this is the last slides on my presentation, still about the basis function. So the global basis function must be chosen such that the tangential components of E are continuous across the element boundaries. So the normal component to the edge is allowed to be discontinuous. So it is natural to associate the basis function with the values of electric field along the edges. So in this configuration, the edge elements have a mixed order of representation. Mixed means that we're going to use functions that are either constant or linear. So within each cell, Ex is constant in the x direction. So we are talking about a C function, and linear in the y direction. So we're going to talk about L function. And for the y component of the electric field is the opposite. So we're going to have linear function in depending on x, and constant depending a constant in the y direction. Our representation using the nodal function, the original one, can be decomposed in this way. So we have a vectorial quantity here, and then we use our edge elements, and we derive these two representation for the two components of the electric field. Note that the edge elements are not complete first order, so they are mixed first order and constant, but represent a subset that is suitable for the curl equation. So this is the last slide. In the next lecture, we're going to apply the edge element technique to the case of solving the eigenfunction in a cavity problem. Talk to you soon.